Hi, this is Wayne Landis. We're talking about our continued work on making a risk and decision-making framework to manage the multiple stressors and endpoints in the upper San Francisco estuary. I'm the speaker, but I represent a large number of other people. We've also had funding from the California Metropolitan Water District, state water contractors, the California Department of System Regulation, and soon the Delta program. And you can find a lot of our other projects at this particular YouTube site. The use of Bayesian networks to calculate relative risk has been published now for quite a few number of years. Here are just some examples of the papers. The Landis 2021 is the current review of what we specifically do. There are many other people who are now working on the use of Bayesian networks to look at risk assessment for a number of different questions and a large number of different sites. This is a very simple Bayes network with the two parent nodes, which just represent any two variables. In this particular case, we have 4 states and a distribution, talking about the frequency of each one of those states. Those interaction between those nodes is determined by the child node. Those interactions are actually governed by the conditional probability table, saying what different combinations of the states of the parent nodes give what output distribution in the child node. This has been around now since the mid-1980s, the use of Bayesian networks. And many other people have pioneered this, and we are also now using it to look at risk assessment. The relative risk model is based on real simple causal pathway. We have sources of stressors that enter a number of regions. We've called it now for habitats, but it's really location, where it can generate effects to very specific kinds of endpoints and create impacts, which are changes to those things that people care about in the environment. So that actually describes the endpoints. We also build into these chemical pathways, often in some ways similar to an adverse outcome pathway. We have in our particular risk region a number of stressors, different chemical groups that generate a variety of pathways. In this particular case, we're going to be looking at the endpoint called fish toxicity. And right below that is the Bayesian network that results from thinking this through. And we'll talk about that next. Our study area is actually the Sacramento Bay Estuary. We have 6 regions that we've broken this estuary into, from Sushin Bay, where it's a lot saltier, and then places up in the Sacramento River in the Delta, where it's mostly fresh water. But 70% of potable water in California actually go through this particular region. It's a very diverse system: urban agriculture, military bases, parklands, large cities, the capital of California. We calculate risk for each one of these regions, and you'll see that in just a bit. Here's the model. You notice over in the far left, we have our risk regions. In this particular case, we're looking at malathion and diazinon and how they interact. To the top pathway, talking about how they will inhibit acetylcholinesterase activity. Depending upon that inhibition, you'll get some mortality generated that feeds into a node called total fish mortality. Through the bottom is Chlorpyrifos and Bifenthrin. We actually use a model we'll talk about just a little bit, talking about mixture mortality when you don't have a single endpoint necessarily or a single pathway. And we're going to combine all these interactions to generate a total fish mortality percent probability. And the 0, 5, 10, 20, 50 that are in there are actually an EC5, EC10, EC20, and EC50. So those are our cutoffs. In the top, the data are from Kathy Letts and her NOAA colleagues, published in 2009. At the bottom is what Hutton and her other colleagues at Oregon State. That paper just came out. For chlorpyrifos, the values that we use to represent So the value on the left is the micrograms per liter, and that's from the dose response curve is appropriate to the EC5. And you can see the different concentrations change, and you get the EC10, EC20, and going, why don't we use the PNEC or some straight thing? Because it's really important to understand what the ranges are. The EC values also often correspond very closely to something like a PNEC or some other threshold value. Also, I want to make it very clear that we're talking about a dose response curve, not a bright line. The way we looked at the mixtures is Eric Lawrence basically invented a mixture models dose response model to looking at different things. He is actually going to publish a technical memo. He has published a technical memo on this. We put it on our website, and we're preparing the manuscript. Basically, the question is, how do you deal with dose response data? So here's just an illustration where the blue line and so forth is the dose response curve for Bifenthrin. The yellowish is Chlorpyrifos, and the EC20 normalized concentration, because we're trying to make this model specifically on the EC20, is the red line. So here we have that line that describes the toxicity of that particular mixture. So that's what we're calculating. In this particular case, if you look over on the far left, we have the confluences or risk region. From those data sets that we have, it plugs in the concentrations of malathion, diazinon, Chlorpyrifos, and Bifenthrin. You notice that Bifenthrin is the one that has the widest range of concentrations corresponding to EC50s and so forth. Go through, we do the calculation. There's a 71% of the fish mortality being equal to or greater than EC20, which a lot of times means it'd probably be over an EC5 or EC10, which is about in the range that people in the past have deemed to be unacceptable. So that's that probability. These are data from that particular risk region, and these are observed data. We ran the same analysis for the other regions. The confluence is the one at highest risk. The second one is South Delta, so forth and so on. So you can see the probability of the toxicity being over that EC20 value. And all of these toxicities are greater than a 30% probability of being over an EC20. What to do about that, that's actually not our decision. But from that, we can run other scenarios and get the dose response curves and see how that changes. Which one of the variables was the one that was most important? Well, the green lines here are the mixture mortality for number one, mixture mortality for number two. Yeah, actually, when you look at the chemicals themselves, the malathion, diazinon, Chlorpyrifos, it's the orange Bifenthrin. That is the chemical that is most important in predicting what the risk is. In this particular case, or contributing to that, providing the information. Acetylcholinesterase activity, which is the combination of those two OPs, is also very important and really driving it. So you can use the sensitivity analysis to start looking at which variables are more important in predicting the final outcome. So the interaction of the chemical mixtures can be estimated and built into the Bayesian network. The building blocks and tools needed to build the rest of the risk assessment. The other chemicals and so forth have been constructed. And next step, I'll see you in Copenhagen, and we'll show you the result. And if you want to see more of what we have done, here's some other papers related to this research. Thank you very much.